For the past 100 years, physicists have been trying to solve a single, glaring math problem. We have two incredibly accurate ways to describe the universe, and they completely refuse to work together. On the largest scales, gravity governs the orbit of planets and galaxies with smooth, predictable curves. But zoom down into the atomic realm, and that predictability vanishes. Down there, the electromagnetic, strong, and weak forces operate under chaotic, discrete rules that look nothing like planetary orbits. When researchers try to combine these two frameworks into one set of equations, the math breaks down, producing infinite, nonsensical answers. The macro and the micro simply cannot coexist under our current models. This century-long stalemate suggests the foundational premise is flawed. The universe may not be a void filled with invisible forces, pushing and pulling on matter. A theoretical framework called Quantum Graph Emergent Field Theory, or QGEFT, approaches the problem differently. It models the universe as a discrete, dynamic network of nodes and connecting edges. This network operates on a single rule: topological optimization. It acts like an engine constantly trying to cool down, searching for the cheapest way to arrange itself. When an area gets too tangled, the network automatically deletes or reroutes those connections to minimize its total energy and structural stress. Every physical interaction we observe is a macroscopic byproduct of this underlying network frantically rewiring itself to save energy. To understand physical reality, we have to look past the objects themselves and focus on the energetic cost of the connections between them. Let's look at gravity. The classical definition tells us it is an invisible attraction between massive bodies, like the Earth and the Moon. In a network, distance is simply the number of connections between 2 points. To lower its energy, the QGEFT network deletes the connections separating massive objects. By removing these spatial edges, the system literally shortens the path between the two masses, forcing them closer together. This missing space in the network is exactly what produces the curved spacetime we observe in general relativity. The exact opposite happens when nodes become too crowded. When dense areas clash, the topological tensions to lower that tension is to inject entirely new nodes into the graph to push the congestion apart, an effect we perceive as cosmic expansion. Gravity emerges as the network's method for taking the cheapest energetic path to relieve the topological stress created by mass. Down at the mid-scale, we encounter electrical charge and magnetism. In this model, charge is a geometric defect in the local topology. This diagram shows two types. On the left, an area with a tightly packed excess of edges, representing a positive charge. On the right, an area with a deficit of edges, representing a negative charge. When you bring these opposite defects near each other, they can share the burden. The network increases the edge density between them to balance out the local mismatch, shortening the geometric distance. But look at what happens when two identical defects are pushed together. You get a local area with far too many edges, creating an unsustainable spike in topological stress. To resolve this clash, the network deletes connections to lengthen the geometric distance between the two shapes, creating the effect of magnetic repulsion. Electromagnetism is the result of the universe constantly trying to smooth out the tension of mismatched geometric shapes. At the extreme microscopic scale, we face the strong force. For decades, particle accelerators have shown that you can never isolate a single quark by pulling it apart from its partner. This animation shows two quarks connected by a thick geometric bond. When these nodes are pulled apart, the bond between them stretches, and the energy cost required to maintain that connection spikes exponentially. At a specific distance, it becomes cheaper for the network to snap the bond entirely and spawn new particles at the broken ends than to pay the energy cost of maintaining the stretched geometry. The weak force, which governs radioactive decay, doesn't push or pull at all. It acts as an emergency topological transformation. When specific rigid geometries crash into high-energy spots in the vacuum, the collision threatens to create a chaotic energy spike. The network mitigates this by instantaneously rewiring the internal shape of the particle, changing its identity to a lower energy state so it can survive the local environment. The nuclear forces function as the network's strict accounting rules, acting as emergency fail-safes against infinite energy costs at the quantum level. The QGEFT framework presents a reality where every cosmic interaction, regardless of scale, stems from the management of geometric defects and topological stress. Whether we are looking at the spin of a planet or the decay of a neutron, the same exact mechanism is at work. Long-range forces, like gravity and electromagnetism, manage the vacuum stress between objects, while the short-range nuclear forces manage the rigid geometric defects inside the objects themselves. From the massive orbit of galaxies to the invisible radioactive decay of a single atom, the universe is not a clockwork machine. Everything that happens is the emergent byproduct of space itself trying to relax.